Hello and welcome to the 5th laboratory chapter for Operating Systems course. The topic of this video is synchronization, which aims to help you understand how synchronous execution of threads can sometimes cause problems and how to arrange execution of these threads with the help of mutex variables and semaphores. Let's begin. When you are programming with threads, some problems that are invisible to the inexperienced human eye may arise when you execute your program. We have seen an example back in Introduction to Threads laboratory study, where value of a variable was printed incorrectly multiple times. In order to fix that code, we had turned a single variable into an array of separate integers. As in another example, let's consider the following code. In this code, 10 threads attempt to add to value of a variable 1 million times, one by one. Normally you would expect to get 10 million as a result of this operation, but this code will almost never produce this output. The reason is similar to the earlier problem. Let's study in details. Remember from computer organization course where increasing a value in computer memory requires usage of 3 instructions. Move the value from memory to local register, increase the value temporarily stored at the register, and write the new value back into the memory location. In this code, you have a single variable somewhere in computer memory. When a program with a single thread, such as the ones you have written in Introduction to Programming courses, attempts to increase value of this variable, it performs the mentioned low-level operations. Now imagine 10 threads doing this procedure simultaneously. Some of these threads, let's say 3 of them, may read value of this variable at the same time into their own registers, increase the read value locally, and all write back the same value without adding up. If this was done sequentially, the result would be 3. But now the overall result from these 3 threads will instead be just 1. It is not easy to estimate, even impossible, how many times the instructions will be scrambled like this during the execution of this program. This is the reason you always end up with a different result. Mutex variables come in handy at such situations. These special variables help programmers define a critical region in the code, where the instructions in these regions can only be executed by a limited amount of threads simultaneously. We may use POSIX semaphores that act as mutex variables. You may think a semaphore is a special integer, which can count up from 0 but can never and ever go below 0. You cannot use basic operators on these variables to modify their values. You must use the functions provided by the semaphore library instead. The seminit function sets initial value of a semaphore variable. The sempost function increments value of a semaphore. The semwait function decrements value of a semaphore. When you no longer need an initialized semaphore, you must use semDestroy function in order to prevent memory leaks. In order to understand semaphores better, let's consider an example here. Assume that you have a semaphore variable which is set to 0 with the help of seminit function. Calling sempost twice on this variable increments its value to 2. Now what would happen if you called semwait function 3 times on this semaphore? This is where the fun begins. The first 2 function calls would successfully set value of this semaphore to 0. But what about the third one? The third call will not set value of this semaphore to -1, but rather block the calling thread. It will wait and wait, stay blocked, until another thread attempts to increase value of this semaphore to 1. Only at that moment, the third semwait call would complete its job and set value of the semaphore to 0 again. Now that we are getting familiarized with POSIX semaphores, we can now use them to design a lock and unlock mechanism in our code. In this design, we will use a single semaphore and assume 0 value means locked and 1 value means unlocked. We will surround the line which increases the variable with the mentioned semaphore functions and construct a critical region. Setting initial value of this semaphore to 1 would mean the critical region is initially unlocked. When the threads reach the SEM wait line, only one of the threads would be able to successfully execute it. Decrease value of the semaphore to 0. In other words, lock the critical region and enter the critical region, while the other 9 will be blocked. When this thread leaves the critical region, it sets value of the semaphore back to 1 again, letting in another thread or itself again to enter the critical region. Executing this improved program will always produce the correct output. Don't forget that defining critical regions may slow down the process a bit, but always ensures correct results will be produced. Defining boundaries of a critical region is also an important decision. A larger critical section means a larger section of the program runs sequentially, which will neutralize the advantage of parallelization. Always inspect your code and define your critical regions as the smallest possible section of code. This concludes the 5th laboratory chapter. If you have any questions regarding the concept of synchronization, you may use the forum and web online course page. Thank you for watching. Stay safe and stay healthy.